All right, in this video, we're going to be looking at the effect of the mass of an object on its acceleration. So I've got three different masses of carts. We started with an empty cart with a force sensor, had a mass of 0.315 kilograms. We added 200 grams, we added 500 grams, and we added 700 grams to get these variations here. And then we collected three trials of acceleration data. We also collected the tension force for each of those different situations, and those are there. If you notice, you might think there's an upward trend for the first couple, but then it drops back down. So it seems like those are just staying pretty constant, which is what we're hoping for. We just wanted to change the mass of the cart and see the effect on acceleration, but keep the tension force constant. This is simply to show that is pretty much happening. So I've got the spreadsheet over here. With that same data, I've averaged the three accelerations together to get this. So let's switch over to look at that. All right, so I want to graph mass versus acceleration. So we'll insert a chart quickly here. We're going to scatter plot again. That gets us that. On our x-axis, our independent variable is mass. Put that in there real quick. Mass, whoops. Mass. And we chose units of kilograms because kilograms are really the base unit for mass. And the vertical axis, that's going to be acceleration. Meters per second squared. It doesn't really look linear. If I had more data points, you'd even see it more. It looks like it's kind of curving a little bit like this. So if you look at that little yellow sheet in the back of your notebook, you will see what to do with that. We need to linearize that data before we find a mathematical model. For that shape of a graph, we want to do 1 over our x values. So 1 over our mass. So I'm going to kind of get this out of the way here for a second. I'm going to graph 1 over mass versus acceleration. So let's just slide over here and make another little chart here. There's that. That's going to be 1 over my mass, and that's going to have units of 1 over kilograms. And to determine those values, I'm not going to do it by hand. I'm going to let the spreadsheet do it for me. So equals 1 divided by my mass. It does that calculation for me right there. I'm just going to fill that equation on down. So we're all set. So I did 1 over my x values, or 1 over my masses. So that's going to be my new x, my new independent variable down there. So let's insert a chart now with that. Scatter plot again. And that is looking to be pretty linear, which is what we're hoping for. We're trying to linearize the data. Let's put our axis labels on there. The horizontal axis, it's not mass anymore. It's 1 over the mass. And it has units of 1 over kilograms. And our y-axis, we didn't change that at all. That's still acceleration. Measured in meters per second squared. All right. Since that looks to be pretty linear, let's go ahead and fit a linear trend line to it. Go to the advanced edit window, drop down and do that. I want to see my equation, so let's do that. There's my equation. I'm going to put it across the top so I can see it all in one line. So that right there is the equation, the slope-intercept form equation for that trend line to represent that data. So from that, we can write a mathematical model for the relationship between mass and acceleration. So my y values are accelerations. My slope, 0.2. I'll look for the units in just a second. So I'm going to come right back to that. Slope times my x values are 1 over masses plus my y-intercept, 0.046. And the units on that are going to be the y value, or the y units, meters per second squared. All right. So that is our mathematical model. All we have left to do is figure out the units for the slope. So rise over run. So my rise units are meters per second squared. My run units are 1 over kilograms. My units for the slope are right here, meters per second squared over 1 over kilograms. We have a mixed fraction. No one likes mixed fractions. Let's kind of take care of that. To deal with a mixed fraction, you simply multiply the numerator by the reciprocal of the denominator. It's going to be meters per second squared times kilograms over 1. Just like that. All right, and then to deal with fractions, you multiply across the top. So you have meters times kilograms over second squared times 1. So when you combine those, it looks kind of like that. You could do meters times kilograms over second squared, or kilograms times meters over second squared. The order of the multiplication doesn't really matter. It's typically written more like that. The reason I wrote it that way is because you probably recognize that from the other video you probably just watched. You learned that a Newton is a defined unit. It's equal to a kilogram times a meter per second squared, which is exactly what this is. So the units of the slope of that kind of graph, acceleration versus mass, are newtons. All of this simplified down to that, and that's equal to a newton. So switching back over here to my spreadsheet, let's update the mathematical model. All those units canceled or simplified down to be newtons. So the slope of this graph has units of newtons. What might the slope of this be based on knowing the units? Well, since newtons is a unit for force, maybe the slope of this graph is force. How will I know? I want to check it with my experimental data. So the slope of point 2 we think might be the force. Well, what was the force causing this cart to accelerate? Well, if you come up here and look at our tension forces, it looks like those are kind of hanging right around 0.23-ish, which isn't really that far off from our slope, which we thought might be the force because of the units. Feeling pretty confident in that. That is kind of a nice thing to know. So knowing that the slope of this graph is force, I can write a more general form of the equation. So A equals, we think the slope is force, and our x values are 1 over mass. And that y-intercept is probably meant to be 0. It's so close, and it seems like that would be the case based on the situation. So this looks like a more general form of the relationship between acceleration and mass. Acceleration is the force times 1 over the mass.